Okay, so today we have Vishnu Jejjala, who will tell us about precision string phenomenology. Take it away.
All right, so thank you very much for the very kind invitation to speak. I'll tell you about some work I've been doing recently on Calabi-Yau metrics that are computed numerically and applications of these metrics. The idea being that we're trying to inch our way towards semi-realistic realizations of the standard model from string theory. So I asked ChatGPT to generate pictures based on my title, and it came up with well, these two images, which are somewhat amusing, but a bit still science fiction-y as far as realizing particle physics from string theory. We were also featured in massive quotation marks via the usual Tired Tirade, the String Theories of Field research program on Peter Voigt's blog this week as this week's big hype. So I'll hopefully convince you that there is some substance to these kind of studies, and that we're really, in fact, inching towards precision string phenomenology in a real way. So we're starting off with non-real world. The objective, of course, is to obtain the real world, but we start off with n=1 supersymmetry. We like to recover the standard model gauge group with the correct matter structure, the correct kinds of interactions, three generations of matter such that the couplings are not identical, and have the story be somehow consistent with cosmology. So the easiest bit of the story is just n=1 supersymmetry in 4 dimensions. We can get this from Calabi-Yau compactification. Because the Calabi-Yau is Ricci-flat, we know that we can ensure n=1 supersymmetry in 4 dimensions. And already using topology, the topological features of the Calabi-Yau enable us to go quite a long way in describing physics. For example, in the standard embedding, which I'll be discussing later in the talk, the difference between the Hodge numbers H11 and H12 is computed by the index of the Dirac operator and tells us about the number of generations of particles in the low energy spectrum. So already purely on topological grounds, we're able to realize some aspects of physics that we're interested in at low energies. And this program was sort of initiated in the mid-1980s by Candelas, Hurwitz, Strominger, and Witten, and since then we've been using the heterotic string in order to realize standard model-like theories. So we have used a new tool to analyze these kind of manifolds. This new tool is machine learning, and I've been playing with machine learning in this context since about 2018. The initial investigations were on complete intersection Calabi-Yaus. We're looking at topology of these manifolds. So this is a zero locus of a set of homogeneous polynomials over products of projective space. And the complete intersection condition and the Calabi-Yau condition are realized as constraints on the numbers which appear in these configuration matrices. There are 7,890 of these configuration matrices describe complete intersection Calabi-Yau threefolds. And the simplest example is the quintic in P4, which is realized as a homogeneous quintic equation in this projective space. So we can start off, roughly speaking, in machine learning. If you have about 10,000 data points, you can start seeing whether aspects of that data set can be learned. So we took these 7,890 Calabi-Yau threefolds described by these matrices and tried to see whether you can learn topological data from the numbers which appear in these matrices. So the initial investigations were to learn the Hodge numbers. And in 2018, we found that we could learn these Hodge numbers with about 90% accuracy. Usually in machine learning, you take an 80%, 20% split of your data in order to benchmark how well you're doing. Use 80% of the data for training and use the complementary set for testing. And we've used various network architectures in order to predict the Hodge numbers based on these configuration matrices as inputs. Since our work, this particular idea has been made much more precise, mainly by work by Urban and Finatello, and they're able to get 99% accuracy for these kinds of topological invariants that you compute from knowing the equations to describe your Calabi-Yau. So these initial investigations suggested to us that certain features of Calabi-Yau manifolds are machine learnable, and the initial features we studied were these topological invariants. We since looked at toric Calabi-Yaus, and the toric Calabi-Yaus are obtained as smooth hypersurfaces in the toric variety, which are built out of reflexive polytopes. These reflexive polytopes, up to 4-dimensional reflexive polytopes, were tabulated extensively by Kreutzer and Skarka, and we've been able to study this data set as well by taking a sample, for example, of 1 million polytopes in 4 dimensions. We found a new formula for the Euler characteristic based on machine learning. So we just fed the machine lots and lots of features of these polytopes and asked to predict things based on the features we fed it. And with Per Berglund and the student Ben Campbell, we found the formula on this page for the Euler character. The Euler character is expressed in terms of the number of points in the polytope, number of points in a dual polytope, number of points in twice scaled up versions of each of these. And this the fact the machine was learning the structure enabled us then, from these particular 4 inputs, enabled us then to use regression to figure out this formula. So the machine was basically useful for pointing out which features were important to realize this expression, and then we were able to prove this expression mathematically. We've also been playing games with polytopes in higher dimensions, and with Per Berglund and Yang-Kui He and Ed Ellie Hayes and Ed Hurst and Andre Lucas, we use genetic algorithms in order to construct new polytopes in 5 dimensions. And these new polytopes often have new Hodge numbers that weren't seen in previous data sets. So able to generate new Calabi-Yaus using machine learning. So inspired by these topological successes, we turned to geometry and want to see what aspects of the metrical structure of Calabi-Yaus can also be machine learned in a similar way. So I'll remind you that Yau's theorem is provides a proof of Calabi's conjecture, but it's not constructive. It just tells us that in each Kähler class there exists a Ricci-flat metric, and we would like to establish that the Ricci-flat metric is indeed obtainable starting from. Seem to have cut out. I'm back. Let me share my screen again.
Excellent. We're hoping you would come back.
Okay, so I think this is where I left off when I cut out. So I was trying to justify why we wanted a metric. One reason to have a metric is to compute the kinetic terms, the Kähler potential appropriately normalized, and then in a general compactification, you would then use this Ricci-flat metric in order to calculate Yukawa couplings based on these normalizations. We're also ultimately interested in questions like moduli stabilization, understanding alpha prime corrections to the geometry, and ultimately supersymmetry breaking in order to get more realistic models. And for all of these purposes, we would like to know the metric. So for now, we had to make do with numerical approximations as we don't have analytic expressions for the Ricci-flat metric. So we'll turn to machine learning as a tool for finding these numerical approximations to the Ricci-flat metric. So this subject of finding numerical metrics on Calabi-Yaus has had some history. People have been looking at this for roughly 20 years now, starting with the work of Hedrick and Wiseman and Donaldson. The machine learning efforts were mostly during the, start off with a paper by Ashmore, Hay, and Overt to find machine learning improvements of Donaldson's algorithm. But the machine learning via neural networks effort was during the COVID years, essentially. And roughly 3 groups, Anderson and company, Douglas and company, and our group came up with numerical metrics in December 2020 in various preprints. Since then, we've been advancing this technology in order to provide software that is usable for this purpose on various Calabi-Yaus. And I'll discuss some work we've done for finding better and more efficient methods of finding the flat metric on K3, and I'll assess how good these metrics are as we proceed. The analytic metrics have been constructed in a few cases. So for the torus, Clifford wrote down the analytic Ricci-flat metric in 1873. I think this is fairly late for writing down a flat metric on a torus, but this seems to be the history of this effort. And then more recently, Castro, Tripathy, and Zimet wrote down an analytic metric on a particular singular version of K3, and I'll briefly mention how our numerics compare to their analytics. Okay, so with these motivations in mind, we'll continue to discussing sissies and geometry and machine learning metrics, and we'll proceed to Yukawa couplings and analytic compactifications. And I'll discuss in the end prospects of future work in this research direction. So I'll be talking essentially about the 3 papers in blue that are written at the bottom of the slide. So this is work in collaboration with Per Berglund, Paris student Georgi Butbaya, Tristan Hubsch, Damian Mayorga Pena, Challenger Mishra, and Challenger student Justin Tan. The names in red are the ones who've done the bulk of the coding and are really responsible for many of our key results, both computationally and conceptually. Georgi and Justin their students will eventually be on the market for postdocs, so please keep an eye out on them. Okay, so I'll be studying various sissies in various dimensions. So we'll start with a torus, which is a cubic in P2. We'll look at a quartic in P3, K3, and various deformations of the Fermat quartic. Then we'll discuss the Fermat quintic and deformations of the Fermat quintic. And then when I discuss Yukawa couplings, I'll be looking at the mirror of 2 cubics in P5 and a quotient of the Tian-Yau manifold. The quotient of the Tian-Yau manifold, Tian-Yau has a freely acting Z3 quotient, which gives a Calabi-Yau with Euler character -6. And this is one of the early manifolds that were used for string phenomenology. Okay, so the metric is obtained from the Kähler potential. We take derivatives of the Kähler potential to get the metric. The metric constructs the Kähler form, which is closed and has the property that the wedge product with the top holomorphic form equals 0. And the Ricci tensor is obtained from taking derivatives of logarithm and determinant of the metric. The Ricci tensor will vanish in this Ricci-flat case. So in machine learning, what we'll do is engineer a loss function, which is going to be minimized such that it's minimum when we achieve the Ricci-flat metric on the manifold. So the initial numerical effort in this direction was Donaldson's algorithm. Donaldson's algorithm starts with the Fubini-Studi metric in the projective space, and it provides a baseline for finding an approximate flat metric to which I'll compare our results. So the starting point is the Fubini-Studi metric in the projective space, and we can pull this back onto the hypersurface embedded in the space. This metric will not be Ricci-flat, as you can readily convince yourself even for the torus. Then we'll work with a basis of degree k holomorphic polynomials on the manifold, and we'll use this to construct a Kähler potential. Using sections of line bundles, the number of basis elements for the quintic, for example, will scale like k to the 4th, where k is the level in Donaldson's iterative algorithm. Because the Fubini-Studi is on the projective space is Kähler, and it's very well understood, we can use the Guidara embedding to systematically obtain metric approximations using this algorithm. And the way we proceed is we construct a so-called balanced metric, and we update this balanced metric iteratively. And as k increases, this balanced metric approaches the Ricci-flat metric. The difficulty with this implementation is the numerical methods of doing this are computationally expensive. The number of sections grows polynomially with a level, as a result, it's a very slow way of achieving a flat metric. So we're hoping machine learning will improve this convergence to the Ricci-flat metric. So that's the aim in doing what we're doing as we proceed. So we also need to now assess how good our flat metric is. So we use various measures for doing this. One way of doing this is to compute the volume in two different ways. One way is metric independent, and one way is metric dependent. So the volume of Calabi-Yau is described by the wedge product, the top holomorphic and anti-holomorphic forms integrated over the manifold. It's also described in terms of the Kähler form wedged together integrated over the manifold. So the latter expression is metric dependent. The two expressions will cancel against each other when we achieve the Ricci-flat metric. So this flatness measure is a good way of knowing how close we are to being Ricci-flat. In addition, because we're working explicitly with manifolds numerically, we need to ensure other features are satisfied. One is that the Kähler form is closed. Another is that because we're working with explicit coordinate patches, we need to make sure that the metric on one patch is consistent with the metric on another patch by checking Jacobian, which connects these different patches, give us compatible metrics. And then we also need to ensure that we remain the same Kähler class we start out with, because Yau's theorem tells us about the flat metric within a given Kähler class. So all of these features we want can be encoded in a loss function, and the loss function will vanish when all of these features are satisfied. Okay, so to do this, we'll use neural networks. So neural networks date back to the 1950s. Yes.
Back to the previous slide. You're always evaluating absolute values, so there are no sign.
That's right.
Issues.
Yes.
I see.
So this vanishes only for the flat metric.
Okay. Yeah, I was concerned about the signs. Okay, thank you.
Okay, so the main tool we'll use is a neural network, and the neural network dates back to the 1950s. Rosenblatt in the Cornell Aeronautics Laboratory, the Naval Research Lab, designed what's called the perceptron model. The perceptron model takes an input vector and feeds this input vector by weighting the different components of this vector into a neuron, a perceptron back in the day. And this perceptron evaluates these things, this input, nonlinearly, and makes a prediction based on that evaluation. So typical nonlinearities are the sigmoid, the ramp function, and the tanh function. But you can use different nonlinear functions for your purposes as well. So the modern neural network has these inputs, but there are multiple neurons in each layer. And these neurons are such that you have a fully connected network such that neurons in each layer talk to neurons in the next layer. And this proceeds layer by layer. So each of the inputs into a given layer are weighted and shifted by some bias. And we want to use the training in order to optimize the parameters which appear in this network, the weights and the biases. So we have some function which takes us from one vector space to another vector space, for simplicity, Rn to Rn. And we act with a matrix on the input vector, and we ship this by a bias vector. And then we evaluate element-wise using these nonlinearities, and then we put the pieces together. And the final layer, for example, could be a summation layer. The number of layers is a parameter that you can tune, and we want to take the prediction of the network and compare it to what we call the ground truth. Oftentimes, the ground truth is when you've tabulated. In our case, the ground truth is unknown. We know when the ground truth is satisfied because the loss function vanishes with the Ricci-flat metric. And then we use backpropagation in order to tune these weights and biases to minimize the loss function during training. So in our particular case, for finding the Ricci-flat metric, we use the fact that the metric is Hermitian and use an LDL decomposition of the metric. And we have two different neural networks, one training on diagonal components and one training on the lower triangular entries. And we implemented this using PyTorch and TensorFlow and JAX and different Python-like architectures used in machine learning. And we then need to choose points to evaluate the metric at. So one way of choosing points is by picking lines in Pn and seeing where these lines intersect the hypersurface. So the points are selected with respect to the ambient space of Frobenius duty metric, and then we draw lines between pairs of points, choose a point where it intersects, and then we choose a collection of these points. And we use this for both training, and we use a complementary set for testing. So Schiffman and Zeldich developed this basic idea for point selection on Calabi-Yau. So for example, the Fermat quintic, I've chosen some coordinates for this, the Z4 coordinate, I think, on the plot. This is a density plot which shows that the point distribution is variable based upon where you are on the Calabi-Yau. So if you choose a different quintic, the Dwork quintic, by deforming the Fermat quintic by one complex structure parameter, we find the distribution of points changes quite considerably. So the point selection is based upon how the manifold is realized in the ambient space. All right, so even with order 10,000 points by training with these number of points, we see that both on the training set and on the complementary test set, the losses associated to the flatness measure, the compatibility between coordinate patches, and the celerity of the metric, these all decrease as you train. So epochs is the machine learning term for one pass through the complete set of training data. So epoch by epoch, we see all of these loss functions are decreasing, and this indicates we're moving towards a flat metric. So another way of maybe finding flat metrics is using Ricci flow. So Perelman famously used this Ricci flow to realize a proof of the Poincare conjecture that every simply connected closed remanifold is homeomorphic to S3. In fact, he proved something more general, the uniformization theorem. The idea is that the fixed points of the Ricci flow are the Ricci-flat manifolds. So we can try to use this as a loss function in order to engineer a flat metric. So in fact, Perelman included a dilaton effectively in his description, so that the Ricci flow equations are the equations of motion you obtain for the variational principle acting on this function. Ricci flow is in some sense like RG evolution of a nonlinear signal model in a string world sheet with a target space metric. And this was already realized in early 1980 by Dan Ferdinand. So this is an old idea in some sense in string theory. So the Kähler-Ricci flow has a solve essentially the Ricci flow equation, which is slightly modified by the dilaton, along with what's essentially a backward heat equation for the dilaton. And the flow automatically preserves the Kähler class of the metric. So that aspect of the loss function is guaranteed. So we can start with a pullback of the Frobenius duty metric on the manifold and solve the Ricci flow equations in order to get to a flat metric. The loss function encodes these equations of motion, and we have preliminary results that indicate that we can get this to work, for example, on the torus. So the flow is able to start from the non-flat metric to get us to the flat metric in a very efficient sort of way. It's much harder for us to have implemented this and do this properly on K3 and threefolds. So we don't have, we have preliminary results. We don't have very, very nice results yet. We hope to publish on this topic sometime this year. Okay.
Vishnu,
Yes.
did you cover the part that once you get the metric, the quantities you could compute?
I'm getting to that. So that's next.
Okay, thank you. Okay,
so the package that Larfors, Lucas, Rula, and Schneider put out, CI metric, is an implementation of this idea of using neural networks in order to obtain Ricci-flat metrics. So the model that they use and get the best results with, I think, is what's called the phi model. So starting off with some seed metric the Fubini-Studio metric generally, you can deform the seed metric by looking at corrections that are induced by some global function on the manifold. This procedure for getting to a flat metric also preserves the Kähler class, so it's convenient for finding flat metric in the cases where there are multiple possibilities for the Kähler class of the manifold. So this package is a very, very good package, and I recommend that you play with this because it's fairly straightforward to install and to use. We mainly use this package for point selection. We'll use the same idea behind the phi model. We'll find a different way of finding the flat metric by solving for phi well, I'll show you what I do. So we use what's called a spectral network. So the previous implementations of the neural network essentially took points on the neural network on the manifold along with the metric which lives at those points on the manifold. The spectral network takes points and then gives us this matrix of functions, and we use this matrix at each point as the training data set to learn this function phi, which will give us a flat metric via the loss function for the network. So this is something we introduced in 2022 in studying K3 and singular versions thereof, and we found that it worked much better at finding the flat metric. So the fully connected neural network sigma measure, which measures the flatness of the metric, is shown in blue, and the spectral network we find is about an order of magnitude better in finding the flat metric in the same number of epochs, the same number of points. This corresponds to about level 8 in Donaldson's iterative algorithm. Okay, so given this flat metric, you want to see how good it is, and then whether we can do phenomenology in a reasonable way using this flat metric. So in order to calculate things of use based on the flat metric, we're sort of lucky, and the Kähler geometry simplifies our life considerably. Because the geometry is Kähler, most components of the Christoffel connection will vanish. The non-zero components are the ones I've listed, and as a result, most components of the Riemann tensor will also vanish, and the non-vanishing components are rather few. So therefore, the Ricci tensor is fairly simple compared to a Ricci tensor for a generic manifold. So given this simplification, what we would like to do is we'd like to compute quantities whose answer we know and see how well the Ricci-flat metric recovers those quantities we know. So I'll be working with a family of singular K3s, or there's singular K3s in the family I'm considering. This is the so-called Cephalou deformation of the quartic. And in addition to the Fermat quartic terms in the first sum, we also have these sums of squares squared to get this homogeneous expression. And for particular values of this lambda coefficient, the metric is the manifold that we obtain is singular, and particular values of these lambdas refer to particular singular geometries are studied. For example, lambda equals 1 corresponds to the manifold, which is locally looks like the torus mod Z2. The 3/4 value is the Fermat quartic mod Z2. And respectively, for these particular values of lambda, there are 8, 16, 12, and 4 singularities of A type. So given these, so we can number the singularities, and we can also compute the integral of C2 for K3. The C2 is related to the Euler density. So the integral of the Euler density should recover the Euler character. The Euler character of K3 is 24, so all of these manifolds should recover Euler character 24, and the Euler density is of course obtained from the metric. So if we start with the Fubini-Studio metric, we find that we get 24 when there is no Cephalou deformation, and we again find with the spectral layer we also get 24 for these non-singular K3s. For these singular K3s, when you integrate the Euler density, you get, based on how many singularities there are, different values for the integral of of the Euler density on the manifold, get 8, -8, 0, and 16 respectively. And these numbers are well approximated by the neural network. It's pretty good for the case where lambda equals 3, where you get 15.77 instead of 16, but it's not so good, for example, for lambda equals 3/2, we get -2 instead of 0. So in some sense, the singularities are the places where the neural network does very poorly. What we notice, yeah.
At the singularity, the metric vanishes.
At the singularity, you get a metric, but the metric, so you take the metric, you compute the Euler density, you integrate the Euler density based on that metric you've computed, and you should recover the Euler character. We fail to recover the Euler character properly when we do this at the singular points. So if you look at these different singularities, lambda equals 3/4, lambda equals 3/2, lambda equals 3, and lambda equals 1, we find that close to the singularity, you're generally performing pretty well. But further, when you hit the singularity, the neural network approximations to the metric are not so good. Roughly speaking, however, the Euler character is given by the integral of the Euler density, even for the singular case, plus twice the number of singularities you've got. And this is because the Euler character of S2 is 2. So these are A1 type singularities that you're resolving in order to get the Euler character that you expect for the non-singular K3. So I've done different metric approximations. The black dots, they correspond to just using the Fubini-Studio metric for these calculations. The blue dots correspond to our spectral network, and the red dots correspond to the spline model I talked about. And we see that the spectral network performs best. However, it doesn't perform all that great at the singular points. So, for example, near the singularity lambda equals 1, this is how the training looks with both the fully connected spline model and the spectral network. We see that even at the singular points, the spectral network performs the best. But if you look at the flatness measure is getting much worse near the singularities. If you look at the y-axis in this plot, and it gets better as we move away from the singularity again. So indeed, the singularities are a bit problematic. And because the analytic metric of Castro and collaborators is at one of these singularities, we're not really able to compare our numerical results to the analytic results that were claimed in their work. So it's one thing we'd like to improve so we get a more direct comparison of how well we're doing compared to these analytic results. Okay, so the next manifold to perhaps study is the quintic. So if you look at the quintic, and we compute the quintic's Euler character in various ways, either with the Fubini-Studio metric, where you're treating the quintic as a toric manifold, or you're treating the quintic as a complete intersection manifold, we find that the answer, we know the answer should be -200, and we find that with the numerics, we're off by about 2% in evaluating the Euler character using our Ricci-flat metric, which was trained with about, I think, 500,000 points. So this is maybe good or maybe bad depending on what manifold you're talking about. If you're talking about the number of generations on a model built on the quintic using a Ricci-flat metric, if you're off by 2%, you get the number of generations wrong in your low energy spectrum. But generically, the standard models people have constructed using these heterotic model building approaches, they're on Calabi-Yau manifolds with much smaller Euler character. So if you're off by about 2% there, you're not doing as badly as you would be in the quintic case. So depending upon the manifold you're using for your potential phenomenology applications, being off by 2% may be good enough or may not be good enough. Okay, so we'd like to do what was advertised in the talk and discuss precision string phenomenology. We know that the Calabi-Yau is an sq3 holonomial manifold, and we're working in the context of E8 cross E8 heterotic string theory. The commutant of SU3 in E8 is E6. E6 will embed generations of the particle spectrum of the standard model in its 27 and 27 bar representations. So an important question then is to determine the Yukawa couplings, describe how strongly low energy fields interact when they're in these representations. The 27 bar cubed couplings, these are topological without the Ricci instanton corrections included, whereas the 27 cubed couplings require knowledge of the complex geometry of the Calabi-Yau space. So in this talk, we're going to focus on the 27 cubed couplings. So given the top holomorphic form, omega, we can, for a given 2-1 form, define an equivalent 0-1 form. And the unnormalized Yukawa couplings, which are quasi-topological, are computed without the metric as a wedge product of the top holomorphic form with these 0-1 forms. This integral depends on the cohomology class, but not the actual representative that you pick. So in order to go from the unnormalized Yukawa coupling to the normalized Yukawa coupling, which is the physical Yukawa coupling in your theory, you, in a general compactification, need to know the flat metric. So we're going to use and exploit a shortcut in computing these Yukawa couplings in what's called the standard embedding. So in general, we want to have a holomorphic vector bundle whose connections will solve the Hermitian-Yang-Mills equations. Deformations of the holomorphic vector bundle will correspond to the complex structure moduli of our Calabi-Yau when the holomorphic vector bundle we pick is a tangent bundle. So the metric on the complex structure moduli space is a Walla-Petersen metric, and using Walla-Petersen geometry, we can compute the normalized Yukawa couplings without knowing the Ricci-flat metric. We'll, of course, compare these calculations of the normalized Yukawa couplings using Walla-Petersen geometry to the calculations we'd obtain for the same quantity using the machine-learned Ricci-flat metric. The shortcut for eliding use of the Ricci-flat metric in computing these normalized Yukawa couplings only works in standard embedding, and this is the case in which we're studying Calabi-Yaus with their character plus or minus 6 in order to get a 3-generation model. The Calabi-Yaus that lead to the standard model in previous searches typically do not use a standard embedding, so they require actual knowledge of the Ricci-flat metric, and just knowledge of the Walla-Petersen metric of complex structure deformation space is not enough. So the key is that physical Yukawa couplings require us to normalize. And to normalize, we construct an orthonormal basis with respect to the Walla-Petersen metric. The computation of the Walla-Petersen metric is, it basically uses harmonic projection coupled with a Kodaira-Spencer map. The Kodaira-Spencer map is a map from the tangent space on the deformation manifold to the first homology of the manifold with coefficients in the vector bundle on top. And we can construct this map fairly explicitly. You just take the transition functions and you see how these transition functions behave when you deform via these complex structure deformations of the manifold. And we're able to then use this Walla-Petersen metric in order to compute normalizations, because in standard embedding, the normalizations are related to evaluations using this Walla-Petersen metric. So we essentially pick an arbitrary basis, we apply Gram-Schmidt to diagonalize kinetic terms, and we calculate the Yukawa couplings by normalizing the unnormalized couplings that I discussed a few slides ago. So let me show you how this worked with various Calabi-Yaus. So before I do that, let me also mention that we can compute the Walla-Petersen metric in a different way using period integrals. This calculation via periods really only works for manifolds with small h21. When h21 becomes big, these period calculations involve solving various Picard-Fuchs equations, and that becomes complicated in its own right. So we'll compare with this other method for calculating the Wald-Pearson metric in the case where H21 is small. Okay, so the first manifold we'll look at is the mirror of the Dirac quintic. So we compute the metric either using this Kodaira-Spencer approach or with the explicit period intervals. We find that the data points that we find with the Kodaira-Spencer approach for different values of this complex structure parameter psi are in accord with the explicit period intervals. The lambda equals 1 point is a singular point in the description of the Dirac quintic. So in a specific point in the moduli space of the quintic, we've got a Gepner model, and Dissler and Green were able to compute the Yukawa couplings in this particular theory back in 1988. And it turns out the Yukawa couplings are powers of this parameter kappa, which is approximately 1.092. And we can compute. We normalize with respect to the Wald-Pearson metric. We get something which is blocked diagonal, which indicates we've diagonalized correctly. And then we compute the Yukawa couplings using the Wald-Pearson from the Kodaira-Spencer map, and we compare this to the calculations of Green and Dissler. And modular typos in their paper, the points all agree, and the errors are extremely small. So the calculation of the Yukawa couplings corroborates known results for the quintic. Another model with another manifold with H21 equals 1 is the mirror of 2 cubics in P5. And again, we see that when you compare the Wald-Pearson metric computed using the period intervals and the Wald-Pearson metric, the Kodaira-Spencer map, the data points lie on top of the analytic curve that we get, and we can therefore compute the normalized Yukawa couplings in this model. The unnormalized couplings were computed by Yoshi and Clem in 2019. So this is a cross-section of the 3D plots that were in the previous slide, and this again shows that the Wald-Pearson metric computed numerically, the Kodaira-Spencer approach matches the period intervals really well, even very close to the singular point.
So, Vishnu, there was some manifolds which are considered more realistic because they're closer to the observed standard model. How are these doing?
Okay, so I'll show you the next model, the Tian-Yau. So this quotient of the Tian-Yau has Euler character -6. So this is the model that Kirkland, Myron, Ross, and Green used in their first string phenomenology models. So this is the Wald-Pearson metric along one direction of the moduli, as computed by the Kodaira-Spencer approach, and using this Wald-Pearson metric, we can take the unnormalized Yukawa couplings and then do the normalization with respect to the Wald-Pearson metric, and then compute the normalized Yukawa couplings. The unnormalized Yukawa couplings here are in red, and the normalized Yukawa couplings are in black. So knowing the normalized couplings are very different from the unnormalized couplings. The normalization shifts their numerical values. So what we've done is we've taken this particular Tian-Yau quotient and we've moved around in moduli space. And here's how the Yukawa couplings change as a function of the moduli. So this epsilon is a parameter which describes motion in this complex structure moduli space in one direction. And these hats represent the fact that we've sort of normalized in terms of looking at, so this is the ratio of kappa 222 divided by kappa 111. So we've used kappa 111 as a baseline here, and we've evaluated these other non-vanishing Yukawa couplings. And we've seen how these vary as a function of motion in the complex structure moduli space. What's very interesting about this is if I just give you the raw values of these Yukawa couplings without this normalization by Y111, we see that there are without moving very far in complex structure moduli space, we're already seeing two order of magnitude hierarchies developing in these Yukawa couplings. So it may be that the kind of hierarchies we see in standard model Yukawa couplings are not totally unnatural. But this is the most complicated manifold we've studied on the high. So I don't know the answer about how these things will behave on Calabi-Yau manifolds that are maybe more reasonable phenomenology, such as the ones that the Penn and the Oxford groups have developed. This is, of course, a direction we want to head in, and I know that other people are also looking at similar things. Okay, so returning to a comparison between the neural network calculations and the Wald-Pearson metric calculations. For the mirror of the quintic, we can compute by choosing explicit harmonic representatives the Yukawa couplings explicitly. So we've used a neural network first to learn the Ricci-flat metric and then to learn the explicit harmonic representatives. And we find that for the quintic at the Fermat point in the moduli space, the calculation we get numerically using the Ricci-flat metric gives us 0.1914, whereas the analytic result here is 0.1923 from period integrals. So these numbers are fairly close, and they indicate that the numerics associated to the Ricci-flat metrics matches the analytics where the analytics exist. So in the case of the mirror of the cubics in P5, something similar happens. So the same plot I showed previously, but I've included these blue, green, and red dots on the plot. The red dots correspond to using a non-harmonic representative. The green dots are the machine-learned harmonic representatives, and the blue dots are the Kodaira-Spencer points. So the machine-learned points work better than just choosing some representative, which is not necessarily harmonic, but the Kodaira-Spencer calculation is best in the standard embedding in matching the known results in the period integrals. Okay, so let me summarize and present prospects for where we're heading. So we produced Ricci-flat Calabi-Yau metrics on K3 and various threefolds. We've computed Yukawa couplings, both unnormalized and normalized. We found the normalized couplings match very well with the analytic results where they're available. And we've used the Kodaira-Spencer approach in the standard embedding to make predictions for what the normalized couplings would be in the Tian-Yau quotient. So this is the first calculation of this in a non-trivial setting. Our method, it works for any SISI and for any H21 in particular. And in the standard embedding, we compare the Wald-Pearson to the Ricci-flat calculations to get similar results for these things. So we'd like to track what happens as we change the complex structure moduli to again explore whether these hierarchies are natural. We'd like to compute Yukawa couplings for toric Calabi-Yau manifolds. This is a work in progress we hope to report on in a few months. So the group, Andre Constantine and collaborators, they've been able to compute Yukawa couplings in a non-standard embedding where the holomorphic vector bundle is a sum of line bundles. And they also find calculations of Yukawa couplings in this context. And that's maybe the more realistic context for matching on to these actual phenomenological string standard models. So we'd like to push our ideas in this direction as well. And ultimately like to test the phenomenological virtues of these string standard models to see whether any of them resemble what we see in nature. And ultimately we're after some first principles calculation of Yukawa couplings corresponding to electron mass in the infrared. I think we're still far from this, but we're approaching this. One way to improve the approach to better metrics and also better couplings and so on is to find a better point selection scheme. And this is sort of exemplified by this notion of probability of Bertrand's paradox. So Bertrand's paradox asks us to select random chords on a circle. One way of constructing a random chord is to pick two random points in the circumference and just draw the line between them. Another way is to choose a random radius and then pick a random point on that radius and then draw the perpendicular. And that gives you a chord as well. A third way is to choose a random point in the disk and let that be the midpoint of your chord. So all of these methods exemplify the so-called principle of indifference. They're all suitably random in a sense. And Bertrand presented this idea in 1889. So the distribution of chords chosen with each of these different methods looks totally different. And they're all descriptions of the selection of random chords, set of random chords. So the question that Bertrand asked was that what is the probability that a random chord is longer than the length of a side of an equilateral triangle inscribed inside a circle? And each of these different selection methods gives us a different answer. So, for example, the first selection method, where you pick 2 points in the circumference, in order to be longer than the length of a side, you need to choose a point on the opposite side. And the probability of choosing a point on the opposite side is 1/3. Similarly, you can convince yourself that the probability of choosing chords by picking a point on a random radius or by choosing a point in the disk, they give us probabilities 1/2 and 1/4. So based on which definition of random chord you use, you get a different answer for what seems like a well-defined question. So the James in 1973 noted that we don't specify the size or position of the circle in the statement of the problem. And therefore, the distribution should be scale and translational invariant. And the only one of these three choices that is scale and translationally invariant is the middle choice, the random radius with a random point that's selected along that radius. So it's the only case in which some other circle drawn inside the big circle has the same distribution of chords as the one in the big circle. So let's apply this idea. All of these selections of points essentially use the Feyerabundel-Hopf map. We pick points in the ambient space. We draw lines to choose points on the manifold. So this is the analog, in some sense, of chord selection by choosing random points on the circumference. So we can, in the case of the torus, we know what the answer is. We can, of course, choose points with respect to the analytic flat metric on the torus. And the point selections, they've got totally different densities, whether you choose them using the ambient space chord selection method of Schiffman and Zeldin that I mentioned, or whether you choose points based on the best answer, the flat metric. So we compare these different point selections, and we use these different point selections to train a neural network to find the flat metric using the Fubini-Study metric in the ambient space as a seed as a starting point. And we find that the training with the pullback to the Fubini-Study metric as a seed is different based on which point selection scheme you use. And if you look at these axes, the point selection scheme where you choose points with respect to the flat metric is a couple of orders of magnitude better in achieving a flat metric than the ambient space selection method that I discussed previously. So, one of the main ways to improve these numerical methods could just be improving our point selection. And one way of doing this maybe is to pick new points as you proceed based on intermediate flatter metrics that you're scanning through as you try to go towards the Ricci-flat metric that you eventually want. So that's one scheme that we're thinking about for improving how we use these numerics in order to study Calabi-Yau. So as work in progress, I hope we'll have more to say about that soon. We aim to put out a package. We would like to put the code out relatively soon. Look for Cynic. It's written in JAX. The name stands for Calabi-Yau metrics, Yukawas, and curvature. It's mirror symmetric, and we hope to have this package for other people to use as well. And push forward in this direction. So thank you.
All right, let's thank Vishnu. Do we have questions? So a question showing I really have no idea about this whole world of machine learning, but like how big is the computer that you use for this, and like how many hours do you train?
So the initial work that we did when finding the Ricci-flat metrics with the neural network, that took a couple of days in order to find these flat metrics. Since then, we've used the spectral network, we've optimized the code, and for a reasonable point selection, it may take 20 minutes. So, and this is done on a laptop computer. This is not anything fancy.
I see. Okay, okay. This is really doable at home.
Yes, it is doable at home.
Nice. Very cool. And you think there's a chance of finding some analytic expressions with more data, or is this really orthogonal to what you're doing?
I think we would like to do this, but I'm not sure exactly how. One thing we've looked at and we're thinking about with some students is to look at the large complex structure limit. So the large complex structure limit, there's this SYZ conjecture, which says that the mirror is a torus vibration over some base. So one thing I do know is what the flat metric looks like on the fiber if it's a torus. Then you sort of reduce the complexity of your problem by a factor of 2 because you need to find a flat metric on the base and put the pieces together and so on. So that may be a way to approach analytics. We can as well try to see how to map the our numerics against the analytics of Catherine and company if we improve the behavior of our numerics at these singular points. That's another maybe way to make contact with this. But if you ask me, how do I will I able to find a flat metric on the quintic? I don't know. That's analytic. I don't know. But those are the ideas I have for how to pursue this question.
I see. Very good. Do we have any more questions? If not, I would say let's thank Vishnu again.
Thank you.
And we can go off the record.